Hello everyone, welcome back to another video of Maths 215. In this video, we'll be discussing limits. Now, I'm sure a lot of you are familiar with limits, but familiar in the sense for real valued functions. As in Math 110, you had functions f of x, where x was a real number. This statement denotes the fact that x is an element of the real number set, or to put it in layman terms, x is a real number. So here we had before Math 110, we had f of x, which makes this function a real valued function. Now, to define the limit for a real valued function, we had taking a limit of f of x, where x tends to x naught, which gives us y naught. Now remember, x goes as close as possible to x naught as it possibly can, but it truly is the value that it goes as close as possible to is quite distinct from x naught, as in they're two distinct numbers. So we test how our function will behave not at x naught, but around as close as x naught as possible, as in we're finding out the behavior of our function as close to x naught as possible. And that gives us truly astounding results. For the real number case, remember, numbers for real numbers are simply numbers in a straight line. Here you have one. I've talked about this extensively in the first video, the real number line. Here you could have repeated numbers, repeated 1.33333. You could have negative numbers, -1, -2, so on and so forth. And here you have the origin, 0. This is what is called the real number line. Now, limits in the case of real valued functions, where you had x go towards a number x naught. Let's say that number is exactly 0. Now, you can approach 0. You have two different ways of coming to 0. From the left, here, you approach 0 from the left, and you have the freedom to approach 0 from the right as well. Here, you're approaching 0 from the right. So I'm sure you've calculated left-handed limits and right-handed limits in your respective Math 110 course. But, so as you can see here, if you've been counting, there's basically 2 degrees of freedom to approaching this point 0. If you have x, if you take, say for example, a limit of a function where x tends to 0, giving you a y naught value. From the left, from the right. Now, things work a little differently for the case of complex numbers. Remember, complex numbers aren't numbers in just a simple number line. Complex numbers are numbers in a plane. Here, our number line was one-dimensional, but a plane is exactly two-dimensional. So, let's draw our plane, our complex plane. Here, remember, is a real part. Here, we have the imaginary part. Let's say this is your point here, z0. Here we have 0. We want to evaluate the limit of the function at z0. So the issue is, before we had the convention of approaching z0 from the right and from the left. But as you can see, this is not a simple line. I repeat again, this is a plane. So you can approach z0 from multiple different directions. You could approach z0 from here, 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 and I can go on forever and ever. So there's basically a lot of ways to approach Z0. Now, this might seem like an issue, but it really isn't. Let's see why it really isn't. Let's first define our complex valued limits, taking the limits of complex valued functions, So taking the limits where Z are complex number, here where Z is an element of the complex number set, or in normal layman terms, Z is a complex number. So we have Z approaching a point, Z0, as I showed so in the diagram that I just erased. We have a complex valued function, f of Z, which gives us W0. Now, I will be telling you some definitions and basically some theorems. Please keep it in mind when doing further questions regarding limits, complex valued limits. So, I start off by stating this. For a positive real number epsilon, there absolutely must exist another positive real number delta. Now, I'd like to show this diagrammatically so that a lot of your confusions are cleared. Now, we stated that for a positive real number epsilon, there must exist another positive real number delta. As in, let's draw our complex plane again, which had our complex number Z0 at the center. Let's say Y at the center. I'm going to say it in a few moments. Y, X. Now, as I said so before, you can approach Z0 from a lot of different directions, not like going from left hand and going from right hand to a point. So there will exist a delta neighborhood. This is what is called a deleted neighborhood. A deleted neighborhood, as in, let me draw it a little better. Here we have this Z. Here we have Z0 as center. Now, for a positive real number epsilon, there must exist another positive real number delta. What is the delta? The delta is the radius of this sort of ball. Now, this is an open ball, as in this ball does not contain the elements which are at the surface of this ball. Okay, this is a two-dimensional ball, and it's a deleted neighborhood. What do I mean by deleted? Deleted as in this ball, this open ball, consists all the elements Z inside this ball except for this element Z0. As in, inside of this ball, you will have all the numbers. of Z which can exist inside this ball. But what deleted means that it will not contain Z0. So to recap, we have for this ball delta as the radius and Z0 as the center of this deleted neighborhood. Now for this delta to exist, we must have a positive real number. We must have a positive real number epsilon. Here, you know that this is Z. This is the Z plane. Z is mapped to W, as we've seen in the definition of complex variables. So we have our F here, which is mapping our Z to W, where in W we had U as the real part and V as the imaginary part. For this delta to exist, we must have a positive real number epsilon, which is also encompassed around a ball with radius epsilon. Here the center is, of course, W0, as by the definition, taking the limit Z tends to Z0 of f of Z will give us W0. Now, the case here is the fact that this is not a deleted neighborhood. This neighborhood will contain W0, which was not the case for this neighborhood. And I would like to point out the fact that for whatever epsilon that surrounds this point W0, there will always exist a delta, a positive real number delta. Thank you, and hope to see you again in the next video.